On the surface, Zephyr is a real-time operating system that competes with the likes of VxWorks, RT-Thread, and NutX. It's not really fair to compare it to something like bare-free RTOS, which is mostly just a scheduler for running multiple threads. Zephyr is more than a scheduler and some libraries. It provides a full build system integrated with vendor development kits and promises fully portable application code by relying on Devicetree and Kconfig systems. It comes with a large array of libraries like device drivers, networking stacks, and graphics drivers. It also ships with this West meta tool that helps build and flash applications along with providing powerful repository and dependency management. We'll only scratch the surface with West in this series. There is a lot going on in Zephyr, which is why it's known as the Zephyr Project, and not just an RTOS. The downside is that unless you have experience developing device drivers for Linux, the learning curve can be extremely steep and frankly overwhelming. But once you get used to it, it becomes easy to build professional-grade, truly cross-platform firmware for your devices. Yes, there is a good amount of overhead, so it's something I'd only recommend for beefy 32-bit microcontrollers with at least around 4 kilobytes of RAM. You'll likely need more than that if you want to take advantage of Zephyr's true powers, such as ready-made networking stacks to build cross-platform IoT firmware. There's so much overhead and such a steep learning curve that I'd honestly only recommend using Zephyr for such projects. For blinking LEDs, reading sensors, and turning simple motors, you're probably better off with bare metal programming or using something like FreeRTOS if you need basic multi-threading. If you still want to learn Zephyr, then you're in the right place. Many vendors are throwing their support in with Zephyr, like Espressif and Nordic, as it seems like the way of the future for non-Linux IoT devices. And speaking of blinking LEDs, that's exactly where we'll start. But first, let's talk about what you'll learn in this series. In this video, I'll give you a very brief history of the Zephyr project and why you should care about it. I'll also walk you through the process of running my Docker image so that you can start developing Zephyr apps right away. I found that installing Zephyr can be quite an undertaking, so I recommend using this image for this series so that your files are in the same place as mine, as we'll be looking through a lot of source code in the Zephyr libraries to figure out how things work. Once you're comfortable with exploring Zephyr and building projects, I encourage you to install Zephyr locally on your system to understand how it's set up. We'll finish this episode by building and flashing a simple blinking LED project to verify that everything is working. In the second episode, I'll give you a brief primer on CMake. Many embedded programmers have some familiarity with CMake, so we won't spend too long here. But Zephyr relies heavily on it to assist with building projects, so it's something you'll need to know. Next, we'll dive into Kconfig and how Zephyr, like Linux, uses this system to enable and disable various software components. It's here that you'll likely start to understand how Zephyr is more than just an RTOS. It relies on a collection of Linux tools to help configure and build projects. If you have experience developing device drivers or kernel modules for Linux, this will likely be an easy review for you. If, like me, you come from a pure microcontroller background, this can take a while to understand, so be patient with it. After that, we'll spend the next few episodes on the device tree. This is often the biggest hurdle for newcomers, as it is an older system with its own language and compiler. We'll go over the device tree syntax first so you can start to get some practice reading device tree source files. You'll also see how the Zephyr build system compiles all of the device tree fragments scattered throughout the source code to produce a final device tree for your project. Then we'll talk about bindings. This is where Zephyr differs from Linux in how device drivers are handled. We'll introduce yet another markup language, YAML, that Zephyr uses to describe the interface between the device tree and driver code. We'll look through Zephyr's analog to digital bindings and code to understand how a device driver is constructed. We use this information to create a simple analog to digital demo. We culminate this section on the device tree by writing our own device driver. It's a very simple button wrapper, but you get to see how Kconfig, Devicetree, bindings files, and C code all work together. You'll also be challenged to write your own simple I2C driver for a temperature sensor. As with any good programming environment, we demonstrate how to perform step-through debugging using OpenOCD and GDB. If you get the recommended ESP32S3 DevKit C, it comes with an onboard hardware debugger broken out to a separate USB port, so you won't need to purchase an additional debugger kit. Once we've built that foundational layer of working with Kconfig, the device tree, and debugging, we can start demonstrating real functionality. We'll start by talking about multi-threading. I'll demonstrate how to configure threads, mutexes, and semaphores. But if you want to dive into multi-threading theory, I recommend checking out my Introduction to RTOS series. Next, we'll briefly go over interrupts, pin level changes, timers, and counters. We'll then look at the LVGL graphics library that ships with Zephyr and how to use it to draw things on a small LCD. After that, I'll demonstrate a simple Wi-Fi connection and HTTP GET request, which should open up the world of possibilities for creating IoT devices. Finally, I'll end with an overview of how to create your own custom board configuration. Zephyr requires you to use a board configuration, which is great if you're using one of the officially supported boards. But most embedded engineers I know want to work with custom PCBs for their chosen microcontroller. You'll need to create custom device tree and Kconfig settings to have Zephyr build for your custom board. We won't get into creating custom chip configurations, but your knowledge from this series should provide you with the foundational skills on how to make that happen. This series requires you to be proficient in the C programming language and have some experience working with microcontrollers beyond Arduino. That means understanding things like pointers, structs, callbacks, registers, and interrupts. While my Introduction to RTOS series is not strictly a prerequisite for this series, know that if you have worked through that one, you're probably ready for this one. If you have experience developing Linux device drivers or working with the device tree, this series will mostly be a review for you, so feel free to skip ahead. Before we install Zephyr, let's talk a little bit about the history. I'm always fascinated by technological timelines, and I like sharing that joy. Zephyr started life as the Virtuoso RTOS for digital signal processors, developed by the Belgian company Ionic Systems. In 2001, Wind River Systems acquired Ionic Systems and eventually open-sourced Virtuoso under the name of Rocket in 2015. In February of 2016, the Linux Foundation announced a new project to build a real-time operating system for the Internet of Things devices. They called this undertaking the Zephyr Project, and it included Intel, NXP, and Synopsys among its early supporters. At the end of 2024, Zephyr version 4.0 was released. We'll stick with 3.7 for this series as it's what was available when I started recording. Since the start of the project, Analog Devices, Nordic, Qualcomm, ARM, Infineon, Renesas, Silicon Labs, ST, TI, and funny enough, Wind River, have all become supporters among many others. I'll be honest, when I first tried Zephyr a few years ago, the installation process and learning curve were enough to turn me away. It's come a long way since then, and lots of silicon vendors are jumping on board. It holds promise to be the open source, professional operating system for relatively small embedded systems, especially IoT devices. That being said, the learning curve has not gotten much better, as it relies on some older Linux systems like the device tree. But that's where this series comes in. I hope to help you get over that learning curve so you can start building cool stuff with Zephyr. Now, let's take a look at the supported boards before we install anything. I highly recommend using the ESP32S3 DevKit C. If not, you can head to docs.zephyrproject.org and go to Supported Boards and Shields. Here you can find the various supported boards for Zephyr, and I still recommend using something from Espressif, one of the ESP32 boards. The reason for that is because early on some of the overlay files, some of the Devicetree stuff, and the code might be a little different depending on what you see in the examples that I'm going to show you. As a result, that's why I recommend the DevKit C for the ESP32S3. Notice here that they have the information about the board and anything else you might need to install. But for example, if you use the S2 DevKit C and you have one of these lying around, a few things might be different. Notice here that we need to install some things from Espressif. When I show you the installation method, if you use the Docker image, this comes with it. If you're installing Zephyr locally, you will need to perform this action to get the closed source blobs for the things like the Wi-Fi driver for the ESP32 boards. If your board is not supported, you're going to have a very difficult time with this course. That's because Zephyr is built on this idea of boards, and the Devicetree connects everything together. So if you're not familiar with Devicetree or creating your own board definitions in Zephyr, it's going to be very difficult. The idea is that by the end of the course, you should have enough foundational knowledge to create your own board definitions, but I recommend starting with one of these supported boards as a result. If you'd like to follow along with this course, I highly recommend setting up a breadboard as I've shown here. You'll want to connect an LED, a couple of buttons, a 10K potentiometer, an MCP9808 temperature sensor, and a SPI LCD with an ST7735R driver chip to your ESP32S3 DevKit C board. You'll also want to make sure that you plug the USB cable into the UART port. We'll use the USB port in a later episode for debugging. Note that you can find all of these components on DigiKey. I'll make sure that my component list contains links so that you can quickly put together your own kit. Check the description for a link to the written guide where I list out all of these components and this diagram so you don't have to pause the video. Even though this says latest for our docs, we're going to be using 3.7.0 for the rest of this course. So you can change that to the version we're using to get the API, the references, the supported boards, all the information for that particular version. If you scroll on up in the docs, you can head to Developing with Zephyr, and there's a really good Getting Started guide here that walks you through the process of installing Zephyr locally on your system. Notice that it supports Ubuntu, which probably means other Debian-based Linux flavors. There's also Mac OS and Windows, and you just follow those to install Zephyr locally. There's one issue I have with this, and that is I can't guarantee it's going to work exactly the same across everyone's computers if you go through this process. And that's because Zephyr likes to be tightly coupled with your operating system because it installs a bunch of generally Linux tools in order to make the build process happen. If you search down here, go to West, and you go to Workspaces, you will find how Zephyr recommends creating your directory structure to develop with Zephyr. In T1, it says Zephyr is the manifest repository. Zephyr was developed with West, where West is a repository version control tool. You can use West on its own without Zephyr, and you can use Zephyr without West, but a lot of the documentation uses both of them together. As you can see here, a West workspace is created, and West YAML files define this workspace for us. In the T1 topology, you set up the Zephyr RTOS repository, the source code for Zephyr, and you develop your applications in that repository. Basically, you would fork Zephyr and then develop in there. There's also the star topology where you have Zephyr be outside of your application, but this kind of assumes you have a single application with Zephyr acting as more or less one of your libraries. One of my issues is Zephyr is huge. It's gigabytes because it contains all of the libraries and HALs for the different supported boards and SOCs. This can be an issue if you're trying to, say, develop a bunch of different applications as you would for something like this course where we're developing simple things over and over again. T1 or T2 topologies work fine if you have one massive application and you want to tightly control the versions among all of your libraries, including Zephyr, using something like West. What we're going to do is closer to the T3 forest topology, where we've got our applications separate in an app folder inside of our workspace. That will be separate from modules, and we're not going to use a manifest file because we're going to keep this separate from West for the time being. We're going to put Zephyr RTOS and Zephyr SDK, which are two different things, in a separate folder on our computer and make sure everything links together. That is how my Docker image is set up, so it all just more or less works for you. But if you're following that Getting Started guide, it will put Zephyr with your applications. Just be aware when you're installing the toolchain if you try to do this locally. As I mentioned, the Zephyr RTOS and Zephyr SDK are two different things. In fact, they have their own separate repositories under the Zephyr Project RTOS account. Zephyr, also known as the Zephyr RTOS, is the source code that will get built and linked whenever you build an application for Zephyr. For example, if you go into boards, you can view all of the supported boards, and let's go down to Espressif. You can see our ESP32S3 DevKit C. This is all the hardware and software configuration files that connect to the device drivers in order to make applications work for this particular board. In addition, under lib, we have all of the libraries that come with Zephyr. We will examine all of these throughout this course. The SDK, known as the SDK-NG, contains all of the tools and tool chains required to make applications build for your particular target. So Zephyr isn't a magical build process. It's a collection of libraries and an SDK that contains the tool chains needed for your target. ARM is very popular, as well as the extensive boards, and if we're working with an ESP32, that's going to be an Espressif chip, which is based on the extensive processor. So we're going to install the SDK that has the build tools and some other helpful tools for us, and we're going to build our application that pulls in the Zephyr RTOS libraries to make an application happen. You are welcome to install Zephyr locally on your computer. If you run into any issues, I might not be able to help you very much because I don't know your specific setup. So to help make this a little easier, if you head to github.com/SeanHemel/introduction to Zephyr, I've created a Docker image that you can just build to create a version of Debian that runs kind of as a virtual machine, even though it's a container. You can log into it with VS Code or log into it from a browser, and everything is just set up for you. I'm going to be showing you this so that you can follow along and have your build system set up exactly like mine. If you're doing this on Windows, you will first need to install WSL. That's because Docker wants to have the WSL backend in order to make all of these processes work. Just head to learn.microsoft.com/en-us/windows/WSL/install and follow these directions. If you bring up a command prompt, I will be showing PowerShell by default. For Windows, you should be able to drop this down and go to Ubuntu, and this is how you know WSL is running, specifically WSL2. That's the Windows subsystem for Linux. Make sure that runs, and then you can install Docker Desktop and make sure this is running in the background so that we can create our image. You will also need to install Python on your host machine so that we can flash our firmware using the ESP tool, which is all Python-based. I am running Python 3.12. Feel free to try something else, but know that that's what worked for me. To get started with this Docker image, go back to this repo, the Introduction to Zephyr repo, and simply click Code and download the zip. Unzip that somewhere on your computer. For me, I put it into my GitHub repository, and everything is right here. To use it, I'm going to bring up my command prompt. Let's get rid of WSL for now because I don't need this. I am in PowerShell, and I am going to navigate to that directory. So let's go to Projects, GitHub, Introduction to, not FreeCAD, Zephyr. From here, I'm going to call Docker, make sure Docker Desktop is running in the background, build-t, and I'm going to give this a tag environment, Zephyr Espressif. I'm going to do -f to point it to the dockerfile.espressif file. That's the instructions on how to build the Docker image, and then which is the current directory for the context, and we are going to let that build. Yours will probably take longer, but because I already have it downloaded and created, it more or less created the image for me instantaneously. If we bring up Docker Desktop, you can see that I've got the image right here and ready to go. Notice that it is still 4 GB, which is rather large. A lot of that is the Zephyr RTOS and Zephyr SDK. Back in our terminal, we're going to run that image. So we're going to go docker run --rm to remove that container whenever we're done with it. Note that every time you fire up this image, it will remove the container so nothing gets saved. Feel free to do it without --rm if you just want to keep the container and you want to make changes to it, but I find this easier, especially when teaching courses and workshops. Then we're going to do -it to make it interactive, should you want to play with it. We're going to map the local port 2222 to port 22 so that you can SSH into it. Note that you need to use 2222 instead of 22. And then we're going to also map 8800 to 8800. That port allows us to access the VS Code server running in the container, and we can access it using our browser. Then we're going to use -v, which is to map a local folder to a remote folder. In this case, the remote is the container. PWD in PowerShell says get the current working directory. Note that this is probably a little different on Mac OS and Linux, where you need to use the PWD command. And that says our workspace, our local workspace, which has our applications in it, map it to root workspace. And I need to use / because that is Linux. Then we're going to set the working directory to workspace so that we, in theory, automatically log into that. And then we want to call the name of the image, which is end Zephyr expressive. So fire that up. And that starts running a server in the background. You can specify an entry point using the entry point flag if you want to just say log into this, but this is now running an SSH server that you can log into, and it's also running an HTTP server that we can just go here. If you are curious and you want to create your own version, take a look at the dockerfile.expressive and you can see the instructions I used to create this Docker image. Specifically, we install the dependencies, set up a Python environment, we install the Zephyr RTOS, which remember is all of our libraries. We also install the Zephyr SDK. My Docker file specifically just installs the minimal images required to get things working and targets the expressive toolchain. So it's leaving off the ARM toolchains, the CMSys, HAL libraries, and anything else that's not part of the expressive toolchain and their HALs and libraries. We also set up a VS Code server that allows us to access VS Code from the browser and install the required extensions. That's essentially what's going on to create this Docker image. Now, if you open a browser window and go to localhost port 8800, you should be presented with a VS Code interface. You might have the CMake extension yell at you, in which case we can just say do not show again. This extension was installed but not necessarily configured for the toolchain in Zephyr, so feel free to tinker with that if you want to. I have that mostly so we can highlight the syntax in CMake files, which we will cover in another episode. You will notice that there are 2 directories in our workspace. The first is this /workspace, which is mounted from our host computer, so any changes you make in here will get reflected on your host machine. That way you can copy it out if you want to keep your code. And there's also opt toolchains Zephyr. This is the Zephyr RTOS that we copied in from that repository. If you go to terminal and you go to the root directory, feel free to take a look at the files in here. You can see that there is a Zephyr code workspace file that defines this workspace for us. And if you go to opt toolchains, you can see that this is where the Zephyr RTOS is installed, as well as the Zephyr SDK. And we will be relying on all of those in order to make the build process happen. This is not the only way to work with Zephyr for this course. If you're not installing locally or you're not going to use this browser, what I actually recommend doing is installing a local copy of VS Code, go into extensions, search for remote, and install the remote SSH extension. That allows us to connect to that container that's running. Down on the left, click open a remote window. We're going to connect to host and we're going to add a new SSH host. Here, we are going to do root at localhost and port 2222 press enter, save that to our local config. You can say connect here, but the way to do this from now on is you click those two arrows again, connect to host, and click local host. That should bring up a new window for VS Code, and I'm going to resize this here so you can see it. And you will probably get asked to continue to store this fingerprint for the SSH. It's going to want the password for the server, in which case it's Zephyr, all lowercase. That is what was set up for the Docker image. Press enter. You'll notice down on the bottom here, it's going to set up the SSH host, and it's going to download and install the VS Code server, which is different than the code server for running that browser or that website interface. This actually needs to match your local copy here. So if you go to help about, you will see this commit. It's actually downloading a version of the server that matches this commit exactly. That's why I can't pre-install it on that Docker image for you. Once you are here, we need to open up the workspace. So go to File, and then you want to click Open Workspace from File. You will be brought into this home directory /root, but go up one to the root directory and you should see zephyr.code workspace. This was copied in from that repository during the image creation process. This is what sets up those two directories for us. You'll probably be asked for your password. It's once again Zephyr, all lowercase, unless you change it. And now, let's close these windows. You should see the two folders over here. I'm going to make this a little bit bigger so you can see it. If you wait just a moment, you're going to get this pop-up. Do you want to install the recommended extensions from Microsoft and Nordic? Yes, go ahead and install. That's going to install 3 different extensions for us. Note that because we've added that RM tag whenever we fired up this image, VS Code and the extensions will get removed every time you shut down that image. Feel free to keep that container around if you want, but for now, I'm just going to install it every single time. This makes it easier for things like workshops, making sure everyone comes from a clean slate. But for you, you can configure it however you'd like. The CMake extension is going to ask for a kit. This is things like the compiler. I have not set this up for the CMake extension, so just click unspecified for now. I mostly have CMake tools installed so that it highlights all of that text in the CMake files, which is fine. Once again, feel free to play around and modify this or customize it to your liking. Let's click on the files over here. So we're back to these 2 folders. Once again, we have our workspace that's mounted from our host machine. So anything you change in here is reflected on our host computer. And then we've got the Zephyr RTOS, just as we saw before in the browser. I'm going to modify this. I'm going to bring this down a little bit so you can see what I'm working on. If you go into apps, you will probably have a bunch of code already written for this course because I created those in the repository and all of the solutions and everything is here. I recommend following along and trying to type some of this out yourself so you understand what's going on throughout the rest of this course, but know that the code's here if you just want to compile and see it working. We're going to start with episode 1. This is Blink. I don't recommend writing the source code and files for this Blink application from scratch because we just want to see if something works for us and we can compile. We will later go through what all of this means, especially things like this Devicetree source, as well as some of the functions found in main. If you get a pop-up for the C, C++ extension, I'm just going to exit out of that one. Note that some of these functions are unique to Zephyr. We're going to go through these later in the course. This overlay file that I just showed is a Devicetree source file that gets compiled with the Devicetree source stuff for our board and our SoC, which is the ESP32 in this case. It allows us to connect application code, for example, in source main. This says, get some information from the device tree. We're going to put it into a struct that's defined in Zephyr for us. And now we can call these functions and pass this struct to our functions, which is kind of like doing object-oriented code, but we're doing it in pure C and we're doing it through Devicetree. It also allows us to write board overlay files for something other than our dev kit, say a custom board or maybe a Nordic board, and we can change how the LEDs or other hardware are connected, and we can keep the source code the exact same. This is what allows for really, truly portable application code, and we will go through this later in the course as we cover things like Kconfig and device trees. You'll see how we are able to create portable code using those systems. This code simply sets up the LED, sets it as an output, and then toggles it on and off once per second. We set up the sleep time here, and we also print the LED state to the console so we can check to make sure that our console is working, which is great for debugging. Let's try to build this and flash it to our board. To do that, bring up a terminal. If you don't have this pane down below, let's say you accidentally X'd out of it, you can go up here to Terminal, New Terminal, and it's going to ask you to pick a working directory. Either is fine, but we want to start with Workspace, because what we can do is just go to cd/workspace and we're back in the same spot. Remember that this is mapped to our host computer, so changes we make here are reflected in the Workspace folder on our computer. From here, we want to go to our apps, and you can take a look at what's in there. So we have O1 Blink, and if you look at what's in here, you probably don't actually have a build folder because that's probably not checked in. So I'm going to go ahead and remove it so you can see what this looks like from scratch. So when you download this code from the repository, you should not have a build folder. We're about to create one using the build system. So all you want to do is west build. So we are going to use west as a meta tool here that tells Zephyr we want to build our project, and it's going to call CMake in order to make that happen. I'm going to say -p always, and -p means pristine, which means clean out the build directory if there is one, or you can remove it manually like I just did. You don't have to do it every time, but if things start to mess up or you start getting weird errors, it can always be helpful to clean out that build directory. Next, we're going to specify our board with -b. We're going to say ESP32S3 _ DevKitC. This means something to West and Zephyr. It's going to look in the RTOS code. So in our Zephyr source code, it's going to use boards. It's going to know to look for expressive, and it's going to look for a board that matches something in here. In this case, this is where that tag is coming from. It also wants us to specify a CPU because the SP32 is dual core and it needs to know where to start running this code. We actually have the option of doing the Pro CPU or the App CPU, but my understanding with an ESP32 is you have to start code in the Pro CPU first before you can start running code in the application CPU. We're not loading in any of the Wi-Fi drivers or anything like that right now, so we're just going to write code that should run on the Pro CPU to keep it simple right now. So with the board specified, we need to specify the processor, which is S3, and then we're going to specify the actual CPU in that module or the processor. So the Pro CPU is what we write here. Note that the board might not be this involved if you're using other systems that don't have multi-core or anything like that, but this is how we have to do it for the ESP32S3 and this particular dev kit. -- says to pass the next parameters. Whatever I say next, those go to CMake rather than West. So West is going to call CMake and pass these next parameters to that. We're going to specify a flag or a variable, so we use -D to do that, and then DTC for the Devicetree compiler overlay file. And this is a special variable that the Zephyr build system understands. It looks for that overlay file that we had specified in our boards, and it's going to apply that to the device tree so that it knows how to connect all of our hardware together. So we're going to say equals from our current directory, which is O1 Blink, we need to go into boards, and then we're going to specify the ESP32S3 _ devkitc.overlay. That's the file that has all that overlay information. So if I bring that up again, this is what's connecting the LED to the GPIO controller 0. There's 2 in the ESP32S3, and 0, I believe, controls pins 0 through 31, and then GPIO 1's the pins beyond that. So we're just going to work with GPIO 0. We're going to talk more about this later when we look at device tree stuff. And we're setting the flag GPIO active high so that the pin goes high when we write a 1 to it in our code. And we're going to specify this label here, and we're going to give it an alias so that we can refer to it in our code. And that's how we get the information here. We get that alias, and that gives us that spec that we've set up here. And we're going to go into more detail for this stuff later. But with this specify, we can now use our board overlay file that connects the hardware together, and we're going to build everything under source. Note that the files here are skeletal bare minimum. You have to have a CMake lists, which define the project. We're going to talk about that in the next episode, how to construct your own version of one of these. Some of the commands you'll find are specific to Zephyr. Just keep that in mind as you're going through these examples. And then we have to have a prj.conf, which is kconfig stuff. Notice this is blank, but Zephyr absolutely must have this file in your application directory. So with that, let's go ahead and build. With any luck, this should build without an issue. So we will just wait for a moment and let that happen. Hopefully you see the successfully created image message with no errors anywhere in this printout. Notice that this created a build directory for us. Because I had tried this earlier, that build directory was already there, but I removed it so that you could see what would happen. If you build again, this should get recreated. If we go into Zephyr, this is the actual output of your build system. Notice that there are things like the DTS, which is device tree information that gets compiled from all over, including the Zephyr RTOS sources, the board definition, your SoC or your processor configuration, as well as your overlay file. Everything gets compiled in this giant file that we will look at later. The other thing you should be aware of is that your .elf and your .bins get produced here. This is what we're going to flash to our board. So knowing that, we can go back to our host system to perform that flashing operation. Remember that we are in a Docker image right now. With some host operating systems, you do have USB access, but in some, like Mac, as far as I'm aware, you don't, which is why you should flash from your host system. So anytime I bring up this console window, remember that I'm no longer in the container. I'm on my host system. So I'm going to start a new PowerShell here, or new terminal. I'm on my host system. This is no longer the Docker container. Let's once again navigate to that directory. I'm going to go to Introduction to Zephyr. And you can see that I've got my workspace. So let's go to that workspace. You can see everything in there. So under Apps, there is O1 Blink. And sure enough, there's that build directory. So I'm going to actually get back out of this. And I'm going to do everything from this directory so that I have access to my virtual environment. And I'm going to show you how to set that up in just a second because Python now requires it. If you are on Windows running PowerShell, you need to call this set execution policy scope current user execution policy unrestricted force one time in order to allow for flashing to happen. Otherwise, you will probably get some errors. So if you run into some errors and you can't flash, try running this if you haven't already. Make sure that you have Python installed. If not, go to the Python website, download it, and install it for your system. We need it running locally. I'm then going to call python-m venv to set up a virtual environment inside of the venv folder. With that, we need to activate that venv. So in Windows, this is venv scripts and activate. If you are on Mac OS or Linux, you will need to call source venv bin activate to activate your virtual environment. You'll know that you are in it because you have this venv in parentheses before your prompt. And now we can use pip to install PySerial and the ESP tool. And I'm using PySerial version 3.5 and ESP tool version 4.8.1 just so everything is consistent if you try to do this course yourself, and hopefully nothing has changed since then. But sticking to the versions helps make sure it's going to work for you if I knew it worked for me. Make sure that you have a USB cable connected from your computer to the UART port on the ESP32 dev board. Then we're going to call python-m ESP tool. We're going to give it the port. In my case, it's COM7 because I checked that before connecting this. So if I bring up Device Manager, if you're in Windows, under ports, I've got this connected to COM7. If you see an error here, you will probably need to go to the Silicon Labs website and install the CP210X VCP drivers to make this work. I'll make sure there are notes for that in the repository. If you're on Mac OS or Linux, this is going to be something like dev tty USB 0 or something. But for me on Windows, I'm on COM7. Chip Auto tells ESP tool to automatically detect the chip. I'm assuming it communicates over UART and says, hey, which chip are you? And then it figures out that it's an ESP32 S3 room, whatever from that. We're going to give it a really fast baud rate here, so hopefully it flashes fairly quickly. We're then going to tell ESP tool to reset the chip into the default bootloader mode before performing any actions, including flashing new firmware. I found that this is helpful for this particular board. Otherwise, you have to reset it into bootloader mode yourself by holding the boot button and then pressing reset or toggling power. We then tell it to reset the board after performing the flash action. And then we give it the action we want to perform, which is write flash. And the flags for that are first -U, which stands for unset the protection bit. This probably isn't the case for the board, but I find it to be useful if somebody has the protection bit locked on the board, and it just makes sure we're able to flash the sectors that we need for writing our binary to that part of memory. I found it necessary to specify flash size detect to tell ESPTool to automatically detect the size of the flash in the chip so that it ensures the firmware is compatible with it. And then we specify a starting address, which is hex 0. That's the very start of flash memory. If you have something like a second stage bootloader or you want to fire up the Wi-Fi drivers, that may be a different thing that we put here. And then it says, oh, go ahead and start the code in the application CPU. But because we're not doing that, we don't have that next bootloader where it starts firing up those drivers. We're just going to write our application directly to the Pro CPU flash and just start it from hex 0 right here. Then we're going to specify the binary. So we're going to go into workspace. We're going to go to apps. We're going to go to O1 blink. Remember that we need to be in the build directory. In there, there's the Zephyr directory. And then we have zephyr.bin. That's the binary we want to flash. With any luck, you should see it writing. And that should go ahead and start flashing our LED. If you have the LED connected to pin 13, you should see it blinking on and off. Let's check the console. So if we go to python-m, because we installed PySerial, we can call that serial library or that serial package. There's tools and then miniterm, which is kind of like minicom, but it comes with PySerial, which is slick because it's truly cross-platform. Specify our device, which is COM7 for me on Windows. And then let's give it a baud rate, so 115/200. You should see the boot messages here. Some of this is from the ESP32, and some of this might be from Zephyr, which we will play with later. And you should see the LED state being broadcast here. So LED state 1010, it's toggling on and off. If you look at your board, you should see the LED flashing, and its state should line up with the messages you see in the terminal. I hope this helps you get started with Zephyr and hopefully helps you understand some of the reasons you might want to consider using it. Learning Zephyr will require grit and likely induce no small amount of frustration, but the payout is quite large. You can use that knowledge to create professional, cross-platform firmware that runs on small, inexpensive embedded systems without relying on Linux. It's quite rewarding when you get there, so take your time and be patient with the process. At the end of most videos, after this one, I will issue you a challenge to take the demo a little bit further. I'll make sure to link my solution in the description so you can check your answer. In the next episode, I'll give you a brief overview of CMake and how it's used in Zephyr. See you then.